Hi guys, now we're going to look at what are binary search trees. So the way the course is structured is like I'll be covering first the concepts, okay, which we need to solve the problems. Right? We required to know first what a tree is, you know, then what a binary tree is, how do you model binary trees, right? We spoke a little bit about n-array trees. Now we are going to see in this lecture what a binary search tree is. This will be the last concept, and then we are going to start solving questions. Right? The way we solve questions also are going to be in a pattern. So agar aap trees, whenever you study any kind of topic in data structures and algorithms, you should always try to solve or understand all the different patterns of questions which can be asked on a particular topic. So when we finish this concept, understanding the concept of trees, we are going to then start solving patterns, different patterns to different patterns which can be asked under the trees topic. Okay, having said that, let's talk about binary search trees. Now, binary search trees, the name search is because this kind of type of binary tree is mostly used in databases. Okay, most of you must have at least heard about what a database is. Now in database, we have the most important job of searching the data, right? Whenever you write a select query, you're going to search the data from this huge data collection you have, and you're going to give the required data, right? Now to make the searching more optimized or to make it very time efficient, we usually have the concept of indexes, right? Indices का concept होता है. Now this indices concept or the entire concept of making the search more optimized, okay, for that this concept of binary search trees is used. Okay, so that's why the word search is there here, because this data structure makes it very it makes it very efficient to search through the large data. So that's why, because of its practical application, the name is binary search trees, right? And why binary? Because here we are talking about binary trees. So we are saying that binary search tree is a binary tree along with some very particular property which it satisfies. So we are going to talk about the property which we call as binary search tree property. Okay, fine. So let's understand what is a binary search tree. So whenever you have a binary tree where it satisfies this condition, let's say this is your parent node, okay, or if because it's the first node of the tree, we can also call it as a root node. This is your left child, this is your right child. Okay, a binary tree is a binary search tree when the left child, all the left children, the value or the data which is stored in the left child is less than the root or the parent. Okay, and your root data or the parent data is less than your right child. What did I say? Suppose if I have whatever data you store in your left subtree, this can be thought of also as your left subtree. So whatever data you store basically in your left subtree, okay, that data is always less than your root, and the root's data is always then less than the right child. Let's try to understand this more through examples. Suppose if I draw a tree like this, and let's say it's 8, let's say this is 3, and this I say 10. Now this does, obey or follow the binary search tree property. What is the left child or the left subtree of this root of this tree? This is 3. 3 is less than 8. Yes, and that's what we wanted here. We wanted that the left child should always be less than the parent. So the left child value is less than the parent. Yes, so it satisfies the first property. Second, we have said that the parent, whatever data which is stored in the parent, okay, that needs to be less than the right child. So what we have here, 8, the data is less than 10. So I can say that this is a binary search tree. Again, why binary? Because it's a binary tree. Every node has at max 2 children. Okay, let's take another example. Suppose if I have here 30 and let's make this as 25. Okay, here we have 23, 27. Okay, here let's make it as 38, 32, and let's say 40. Now let's say whether is this a binary search tree? Let's ask ourselves this question. Look at this. This is your root, right? This entire is your left subtree. What is this? This is your left subtree. What can I talk about this? This is your right subtree. Now, your binary search tree property, which is basically that your left child needs to be less than the parent node, and your parent node basically needs to have lesser value than your right child. This should be satisfied for each and every node of your binary tree. Then only we can call it as a binary search tree. Let's try to check. Let's start from the first. Now 30 value is greater than 25 and 30 value is less than 38. So yes, this particular root node does satisfy the property of binary search tree. Let's talk about this. So let me put just a tick mark so that we know that this has been satisfied. Look, then let's look about this. 25. Now 25 value should be greater than the left child. What is the left child of 25? 23. Yes. And this 25 needs to be smaller than the right child. Yes. So this is following. Also, if you see, this 25 is obviously less than 30. Also, this 23 is less than 30. 27 is also less than 30. That means all the nodes which are here, which are to the left of the parent, all of them needs to be lesser than 30. correct? For some time, if somebody tells, suppose, let's say I make this as 31. Now, is this a binary search tree? No. The reason being 31 is not less than 30, right? So all the nodes which are, to the left of 30 needs to be lesser than 30. So might be, if you put 31 here, it does satisfy the property for this subtree, right? 25, 23 and 31, but it is not a binary search tree. It violates binary search tree because ये 31 जो है, it is greater than 30, but our rule is that this whatever nodes are which to the left of 30 have to be lesser than 30. Okay, I hope I make this point. So now I can say that for this particular left subtree is basically a valid binary search tree. Now let's talk about the right subtree. 38 is greater than 30. So let's first check all the values which are to the right of 30 needs to be what? Greater than 30, right? So is 38 greater than 30? Yes. 32 greater than 30? Yes. 40 greater than 30? Yes. So it does satisfy the property that all the values which are to the right of 30 needs to be greater than 30. Correct? Now let's talk about each and every individual node. Is 38 greater than 30? Yes. Now what about 38 now? 38 needs to be what? This value 32 needs to be less than 38. Why? Because the left child needs to be less than the parent. Fine. And the left child and the root parent node needs to be what? Lesser than the right child. Correct? So this itself also satisfies the binary search tree. Entire node tree satisfies binary search tree. So now I can say that T is a valid binary search tree. Do you get my point? Now think about it for a moment. Where will you always find the minimum value? If I tell you minimum value in a binary search tree, which always will be the leftmost node, correct? 23 is the minimum value in the entire binary search tree, correct? And where will you find the maximum value in a binary search tree? It will always be in the rightmost side of the tree, right? This is always going to be your maximum value for this thing, and the minimum value is always going to be at the left hand side and maximum value is always going to be at the right hand side. Why? Because if you look at these equations, your right child is always greater. Correct? Left child is less than parent node. Parent node is less than right child. So who is the greater? Right child. So if you want to find out always the maximum value will always be in your right hand side. Minimum value will always be in the left hand side in terms of binary search tree. Okay. Now, how it does apply in the application of DBMS, it's not very much important for us to understand now. We can look at it sometime later. But for now, what is important is to understand what is a binary search tree. So binary search tree is very simple. It's a binary tree. Okay, that means all the properties which we have thought about binary trees does apply for a binary search tree. Along with that, it needs to follow these two properties. Correct? Every left child needs to be less than its parent node. Every parent node needs to be less than the right child. Also, one more thing. Let's say you are looking here. Then all of its left subtree needs to be, all the nodes present in the left subtree needs to be less than the root node. All the nodes which are present in the right subtree needs to be what? Greater than the 30. Okay, that is a binary search tree. I hope this makes sense. Now, about representation of this, again, it is the same thing. You can again use classes and objects, same which we had used for, trees. We can use it for binary trees. We can use it for binary search tree. Only this has an extra constraint here. Okay. Now, one more thing which actually we missed when we're talking about trees, okay, binary trees in general, and let's talk about it, is the concept of leaf nodes. Okay. So when you have a binary tree, a leaf node is a node in a binary tree which has 0 children. Okay, let's give some numbers here. So what are the nodes here which do not have any children? This is a leaf node. So 4 is a leaf node because it doesn't have left or right child. 5 is a leaf node because it doesn't have left and right child. 3 is a leaf node because it doesn't have left and right child. So in this tree, I have how many leaf nodes? 1, 2, 3. These are leaf nodes. So obviously, if these are leaf nodes, the ones which are not leaf nodes are called as non-leaf nodes, right? Because they are not leaf. So 1 and 2 can be thought of as non-leaf nodes, right? And these are basically your leaf nodes. So leaf nodes are nothing but those nodes who do not have any children, who have 0 children, can be thought of as leaf nodes. In other words, when you represent this in a class, the left of it, right? Remember, this is a node. So the left of it is equal to null, right? Because there's nothing there. And the right of this is also equal to null. In other words, in the code, I would know this. If a particular node has left equal to null and the node of the right is also equal to null, then I can say that that particular node is a leaf node. Now, this concept is valid for your binary trees and also valid for your binary search trees because we're talking about binary tree in general. Okay. And I hope this makes sense when it comes to binary search trees. All right. We'll so see more about binary search trees when we do questions regarding binary search trees. But for now, you just need to know that it's a tree. It's a binary tree which satisfies these two conditions. Okay.